Hey everyone! Tukoa back again with another crazy video, which means that I have a test coming. Yes, tomorrow I have a test, physics, experiment. Oh my god, this is gonna suck. Yeah, there's gonna be 4 modules, and each person will be getting only each one. I hope I get the easiest one, which is number 1, which is about inertia. The second one is about Hooke's law. And number 3 and 4 is about fluids. Fluids! Yay! We love fluids. Actually, no, number 4 is really easy. I hope I get number 4. And yeah, the purpose of this video is me trying to understand what the hell is going on. And hopefully some random guys from YouTube sees this video and like, oh, I should check this out. And yeah, shout out to that guy. Hi. Hello, what's up? Welcome to the video. Anyways, let's begin with number 1, inertia. Oh, inertia in the context of rotational dynamics. Yes, 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 very cool. Okay, so the goal of this experiment is to calculate the moment of inertia in a homogeneous rod using the parallel axis theorem and and from the period of oscillation. Okay, this is cool. This is cool. Okay, so we have a rod, small rod. Okay. If we rotate it from the middle axis with the length being L, this is the where it spins, yeah, we know the moment of inertia is equals to 1 over 12 ml squared. Okay, where does this come from? There's a proof with calculus. I don't understand. I'm just gonna memorize this. And then the parallel axis theorem, the parallel axis theorem basically says if you move the thing by a few meters, the new one is proportional to that. Let's see using this example. Okay, we're gonna move the spinny part until at the end. Okay, now it spins here with length is still L. And the parallel axis theorem is the new moment inertia, let's use T, is equal to the old moment of inertia plus the mass times the distance. Now the distance here is from the old one to the new one, so it's this, which is L over 2. Cool. Okay, so let's just put in numbers. 1 over 12 ml squared plus ml squared over 4. We can write this down as so ml squared plus, that's 4 by the way, sorry, holy. Well, let's multiply it by 3 so we have the same number at the bottom. Yes, ml squared over 12, and then we can add this to get 4 ml squared over 12 is equals to 1 over 3. Banger. Amazing. Alright, cool. That's the moment of inertia. Oh, but that's wait. Oh, okay. So there's gonna be 2 ways of finding. This is the first one using calculations, and from the experiments we're gonna do I don't know the English word for this. A bundle. What's a bundle? You know these things, and like tuk tuk tuk. Yeah, it goes back and forth. Yeah, okay, basically that. But this time with a stick, like so. Hold on. I'm gonna speedrun. I'm gonna speedrun this off quickly. Okay, so basically it's gonna be a rod. I'm just gonna draw a line. Actually, no. And oh my god, that's horrible. Okay, so this is gonna be the point of rotation, and it's gonna make angle theta. Now the period of this will be equal to 2 pi times the square root of the moment of inertia divided by its mass, gravity, and the distance. Okay, where did this come from? I think I know. Okay, so here there's mass m g, and therefore this will be m g. Wait, is this sine theta or cosine theta? I think this is sine theta. Okay, sine theta. Okay, mg sine theta here is the recovery force. But since we're looking in the context of rotational dynamics, then assume this is d. The length from the rotation to the point of mass is d. We'll get negative because it's like acting as a recovery force. So it's going back, going to the opposite way of the z of the yeah. Anyway, mg sine theta multiplied by d is equals to the moment of inertia multiplied by alpha. Cool. Now if we move this to the right, we'll get the moment inertia multiplied by alpha plus mg sine theta d equals to 0. Now, for very small angles of theta, which is preferably less than 10 degrees, we can approximate sin theta as theta, right? Cool. So we'll get the moment of inertia multiplied by alpha plus mg d times theta is equals to 0. Now there's this thing in oscillations. Basically, if we have a double derivative of something plus a coefficient multiplied by that something is equals to 0, this will always be omega squared. It will always be omega squared. Now alpha is actually the double derivative with respect to time to theta. So as you can see, we're getting really close. Now we just have to divide everything by the moment of inertia, so we'll get there. Yeah, now we have the form here. I theta equals 0. Now this entire thing is omega squared. Let's write this here. Omega squared is equals to mgd over I. Omega squared is 2 pi over t multiply is equals to the square root, because we're, yeah, there you go. So this disappears. Mgd over I. So we'll get t is equals to 2 pi. Oh shoot! But okay, I'm just gonna continue. 2 pi of I over mgd. Okay. Yay! We got it. So basically in the experiment we will square this to get t 4 pi squared times I over mgd, and we solve for I basically. Okay, cool. We solve for I. Easy. And alright, wait, I'm gonna read this again. Yeah, that's basically what we do. That's it. And then we compare this result with this one to get the error. Hopefully a small error. This doesn't seem too bad, like compared to the other ones. So yeah, this is not that bad. I'd like to get this one really. Yes. All right, that's number 1. Wow, super fast. 10 minutes. That's moment of inertia. Yeah, I think that's everything. That should be everything. Oh, this by the way, if anyone's watching this, I don't know. This is just additional information of where this came from. Yeah, this is where. It's not too bad. Yeah, shout out to teachers for teaching. God bless teachers. We love teachers. Yeah, but in the end, this is the rumus, and it came from this. Okay, cool. Number 2, Hooke's law. Oh, by the way, I have a book on my lap, so yeah, if I go quiet, I'm reading that book because I'm low-key confused. Hooke's law. Yes, Hooke's law. Hooke's law. The Hooke's law, if I remember correctly, there will be no questions about oscillations. There will be 0 questions of oscillations. Yes, okay. Thank God. So basically, Hooke's law states that if you have a spring, and then you pull it with a force, it's gonna turn longer, right? Now the size of this force is equals to k, the coefficient of the spring, multiplied by x. This is x, the change in length. Alright, cool. Oh, okay. So in experiments here, oh, sorry. In the experiments that I will be doing, oh, sorry. It'll be like this. We'll have a spring attached to, well, not really a ceiling, but it's gonna be floating and hanging down. We'll take this as L null, and then we will add weight to it. That weight is the F, and it will cause the spring to extend, and then we need to calculate the difference in length to find the K. Alright, cool. That doesn't seem too difficult. So later we'll get data of L null. L null, we'll know what that is. It'll always be the same. And then we'll get delta X, the difference in length after we add the weight here. And then we're gonna gradually increase it. So we'll get different datas of delta X here, which later could be dotted out in a graph of F with respect to X. I think that's what you call it. And then hopefully we get a linear graph with intersection at 0.0. Now this graph has a gradient. It can be calculated using tan theta. And here, the gradient here will always be constant. And this is what we call the constant of the spring. Yes, okay, cool. I don't think I'm gonna go really deep into this. I already made a video on elasticity. If you wanna check that out, yeah, yeah, promotion. God bless promotion. Anyways, yeah, there's gonna be 2 types of springs. And it's not an experimentation, but I think they're gonna ask it in theory. So there's gonna be a parallel one. Oh shoot. This is an object. This is a ball. Ball. And then there's gonna be a series. Spring 1, spring 2. I already discussed where we'll get the rumus, or where we will be getting the equation. But basically for this one, the K will be equal to the total of K1 and K2, with this being K1 and this being K2. And this one, it's 1 over K. 1 over K1 plus 1 over K2. Okay, I think that's it. Looking at the experiments here. Yeah, we'll just add weight to a hanging spring, and we'll calculate the difference in length, and then we'll point it out in the graph, and then we'll get the gradient, which is equals to K. Okay. So yeah, the goal of this one is to find to learn Hooke's law. With this is Hooke's law, and to find the coefficient. And for this one, sorry, I neglected it. The goal is to compare it. Oh, I already said it. Oh my god, I'm going crazy. Okay, yeah, to compare the results from the parallel axis theorem and from the bandul. Yes, I don't know the English word. Sorry. Okay, I'm speedrunning. I have other tests. Number 3 is about, I think, fluids. Okay, fluids. Static fluids. Fluids in rest. At rest, sorry. Fluids at rest. Fluids at rest. Okay, so far, I'm understanding everything. Yeah, I understand this. It makes sense. This makes sense. We're just comparing the values. Okay. This also I already made a video on this, 1 hour long. Yeah, okay, fluids. I hate fluids. Okay. The goal for it is to study, I don't know the English word, I'm just gonna say the Indonesian, hukum pokok utama hidrostatis, and to find the the density, yes, the density of the fluid using a U pipe. Hold on, let me read this a little bit. Okay, cool. So we'll have a U pipe with the same size, same diameter at every point. Sorry, inaccurate drawing. Okay, but first of all, let's look at hydrostatic pressure. Okay, if we have this thing, this is water, and then there's some object at at kedalaman at the deepness of h, we will find that the object is experiencing pressure known as hydrostatic pressure, which is equals to rho g h. Where does this rumus come from? um I think I know, this is my own theory, but okay, we know that pressure is equals to the force over A, which is the area, right? So if we look at here, this is just a volume of water on top of the ball. So F, oh sorry, so there's gonna be a mass, right? Yeah, so the mass of the water is gonna push it down with respect to area. Now, with the densities equation, we know that mass is equal to the density multiply the volume, and we know that the volume is equals to the area multiplied by the height. So we'll get rho AH multiplied by G divided by A. We can cross this out and we'll get rho GH. Okay, in pascals. Also, there's this thing called absolute pressure, which is basically hydrostatic pressure plus one more here from the air, which is usually written as P null, which is equals to 1 atmosphere. This is 1 atmosphere. Alright, cool. We know hydrostatic pressure now. So imagine we have a U pipe filled with water on this part, and then there's also another mystery fluid here, this part. So there's two fluids. Let's assume this as rho 1 and take this as rho 2. Now, the law states that at every point at the same horizontal line, it will experience the same hydrostatic pressure. So here, let's cross the horizontal line here. The hydrostatic pressure here will be equal to the hydrostatic pressure here. So let's write this as H1 and let's write this as H2 as the height. We'll get rho 1 GH1 is equals to rho 2 GH2, and we can cross the G out and we'll get rho 1 H1 is equals to rho 2 H2. Excuse me. Now in this case, we will be using water and spiritus. I don't know what that is in English, but yeah, spiritus. Rho AHA, A for air, well, water, W, but yeah, Indonesian, God bless. Rho SHS. Now we're trying to find the density of the spiritus. So to solve for rho S, we'll get rho A multiplied by HA over H over HS. Okay, now as you can see, this looks like a linear graph. It seems like, hold on. Yes, it is in fact a linear graph. So basically we're gonna get data, graph it out, and then wait. Oh, okay. So we take rho A as 1 gram per centimeter cubed. So this is basically 1. We don't have to write this. So we'll just get this, which is equals to the gradient if we graph it with HA over HS, I think. Yeah, HA to HS. So basically, in the experiment, we'll be adding more and more spiritus into the U pipe, and we'll find the change of height every time and collect the data and point it out on a graph, and we'll find it. And the gradient is equal to the spiritus if it's HA with respect to HS, because we take rho A to be equal to as 1 gram per centimeter cube, which, you know, if you multiply it by 1, nothing changes, right? So yeah, it's basically that. Cool? Cool. Yeah, hold on. This is really weird. Oh yeah, we just solve for rho S, which is rho A multiplied by HA over HS. But we take rho A as gram per centimeter cubed, so it's actually 1. 1 multiplied by HA over HS, that's basically HA over HS. Now HA over HS, if we graph it with HA over HS, that is actually the gradient of this graph. So, oh, okay, so the gradient is equals to the density of the spiritus. Okay, I think that's it. Okay. Oh, and then we have to find the absolute pressure using... Oh. Okay, wait. So, absolute pressure, right? PO is equals to 1 atm or 76 centimeters of mercury. Now the task here, or 100,000. This is a approximation, by the way. It's not actually 100,000. It's like 101,000 Pascal. Okay, the task here is to find in the laboratory what is the pressure of this one if it's like a certain height. Okay, so let's say the teacher says like, oh, the height of the mercury is 60 centimeters. How many pascals is that? Basically, you take this 76 and then divide it by 60. The thing that we know, and then this is equal to 100,000 Pascal divided by X. What is the new value? So basically, this is the same, and this should be the same. Cool? Cool. Yeah, if you do some math, you can solve for X. Yeah, you can solve for X. We know how to solve for X. You just multiply like this. We'll get 76.8. X is equals to 6 million. X is equals to 6 million over 76. We're allowed to use calculators, so yeah, I'm just gonna... Yeah, I have my calculator, it's cool. And yeah, I think that is it. Alright, cool. Alright, last one. Oh my god, under 30 minutes? That's crazy. This is still fluids, but this time it's Archimedes. And I quote the guy who said Eureka while showering. Yeah, fun fact, guys. Archimedes, I don't know. So basically, he was showering one day. No, he was in a bath, actually. And then he was like, wait, if I put in something, the water displaced is equals the volume of that something. And then he just ran around naked, like, Eureka! I solved it! Because it's actually really cool. So basically, the goal of this module is to find the density of the fluid and to study Archimedes law. Okay, cool. Wait, hold on. Okay, cool. So basically, first theory. Assume we have a volume of water with V. And then we put in something. And then the height is gonna get higher, right? Because there's something in there. Now, this height, it's very slight. Yeah, this height, let's say delta H, will be, oh sorry, the volume displaced. So this entire upper thing here, this volume is equals to the volume of the object. Now in the lab, it'll be a beaker glass with milliliters on it, and then you put it and then you put stuff in it, and then yeah, that's it. I think if I remember correctly, 1 milliliter is equals to 1 centimeter cubed. Hold on, let me Google this. 1 milliliters to centimeter cubed. Yes, 1 milliliter is equals to 1 centimeter cubed. All right, cool. This is how we find the volume of the object. Anyways, oh. Sorry. This is how we find the volume of the object. So you might be wondering, why do we need the volume for? Why do we need the volume of the water? Basically, Archimedes' law states that if an object is submerged in water, it will experience a force going up called gaya apung. In Indonesian, I don't know what it is, floating force, I guess. So imagine we have an object that's submerged in water. There's two forces here, mass, mg, and two, the Fa. I'm gonna write as Fa, kan apung. A for apung, yes, Fa. Now, what is Fa equal to? Archimedes states Fa is equals to the weight of the water displaced. So yeah, let's calculate that. Fa is equals to weight of the water displaced. So the m is gonna be different. Divided by g. Now the m of the water is equals to the rho of the fluid multiplied by the volume of the object, because the object is displacing water, and as we know here, the water displaced is equals to the volume of the object. So yeah, multiplied by g. And yeah, that's it. That's the equation. Cool? Cool. Alright, but another way to do this is from experiments. Okay, cool. So first, we will examine the weight of the object at air. It will be W. And then we'll observe the object underwater. This will be equals to W accent. W accent here will be smaller than W because of the floating force. So W here is actually equal to the to the wait pause, hold on. Oh, W, this is a W idea for weight. Oh shoot, W minus Fa, and to solve for Fa we'll get W minus W accent. Now this is the same, so let's just connect that really quick. Rho F V0 G is equals to weight 1 minus weight, oh, at air and at water. Okay, now to solve for the fluid, we'll get rho F is equals to mass minus mass in water multiplied by G divided by V0 G, then cross this out, and you'll get is actually the difference in mass in air versus in water divided by the volume of the object. Okay, in experiments, we'll find the volume. We already know how to do that. And then we'll find the mass. And then we're gonna graph it. Oh, okay. Okay, as you can see here, it's something divided by another something, right? So if we graph this, well, we love graphs with V0 as the x-axis and M1. It's gonna be a graph, a linear one, and this gradient is equals to the will be equal to the density of the fluid. All right, cool. Yeah, fun fact, guys. That's it. What else? I think that's it. Oh my god. Oh my god, that's it. That's it! Oh, hell yes. A 30-minute video. That's actually really surprising. Yeah, I think I understand everything. I hope I'm ready for tomorrow. Well, I'm definitely gonna keep studying, especially for doing the experiments. Like, but theoretically, on the theory side, I think I'm chill. Yeah, if you wanna check out hooks a lot more in detail, I explained it in my elasticity video. Yeah, I'm not gonna explain it too much here. This is foods at rest. This is Archimedes. Yeah, I think that's it. Thanks for watching, guys. Pray for my tests tomorrow. That's it for me. Yeah, bye bye. I'm gonna eat now.